Where's the line between chance and design? Why is there so much junk in our DNA, those regions that seem to do nothing? Is it possible to reproduce evolution not millions of years later, but right now? And how did life begin? We don't have an answer to this last question yet, but we can create an experiment that models the mechanisms of evolution from scratch. Today, you are invited to look inside one of these experiments. It is called GUCA, or Graph Unfolding Cellular Automata. GUCA is a cellular automaton, like Conway's Game of Life, for example. It has living cells and simple rules that make together a model of living behavior. Unlike the classical cellular automaton, GUCA is implemented on graphs. In GUCA, the two-dimensional grid is replaced with a graph of any shape, and graph nodes are analogous to cells in biology and classic cellular automatons. Graph edges define the connections between nodes. This way, they are becoming a model of a multicellular organism. Beyond GUCA, the artificial life community explores a range of engines. For example, Physics World, with multicellular organisms controlled by neural nets. NCAs stay on grids and train the local rule, end-to-end. Taken together, they outline three complementary philosophies: physics first, alien, differentiable rule, NCA, and program as genome on graphs, GUCA. So how exactly do those rules, or genes, work? The genome describes how nodes will behave. Every rule in it is structured identically. There's a condition when the rule is triggered, and an action what to do. These rules operate step by step, and they are what cause the graph to grow or stop. Now let's look at how this works in practice. We're starting with a single node in state A, and the rule: give birth connected A, with the conditions current equals A, prior equals unknown, and parents less than 5. In the first step, it creates a second node and connects to it. In the next step, the new node does the same. Thus, a chain of 7 nodes gradually grows. After this, the parents less than 5 condition is no longer satisfied, and growth stops on its own. We've just seen how a manually created rule works. But in GUCA, you can do it differently and let the rules evolve on their own. It all starts with a random sets of genomes, different kinds of rules, that probably won't make a good graph just yet. Each of them plays out its own life. A simulation is launched, and we see what it creates. The algorithm measures its results against a fitness function. It contains different criteria that imitate harsh conditions of the natural habitat. The most successful structures survive, and the unsuccessful ones disappear. A new generation is formed from the survivors. Some rules are copied, unchanged. Others mutate slightly, adding, removing, or changing one of the conditions. Then this process is repeated over and over. Through many repetitions, genomes slowly develop a feel for the behavior that works best. This is digital evolution, when behavior arises not from design, but from selection and randomness. All the organisms, or graphs, we created in GUCA can be seen live in the sandbox, our website. It contains the first forms: digital organisms, hand-coded. For example, dumbbell, a simple 2-link structure; hairy circle, a circle with branches. Also, we can edit and recombine genes of any graph. That's how we created a hybrid of dumbbell and hairy circle. And there are also the results of real evolution. Triangle mesh, a triangular mesh that emerged without manual adjustments. And quad mesh, a more complex, stable version. The simulations are interactive. You can stop the process, examine each node, delve into its genome, and even disable some rules. There's also a scissors tool which you can use to cut connections and observe how the system reacts. When a system lives long enough, it begins to exhibit effects familiar to biologists and anyone who has studied biology since school. First, regeneration. Some structures are capable of recovering from partial destruction. Connections are rebuilt, and nodes seem to heal like a wound. This is best seen on the website, in one of the fractal organisms. Second, correlated features. In one experiment, a green gene emerged not a true color, but a side effect of a mutation. If it is turned off, the color changes to yellow. But not only that, this gene is actually responsible for the growth of additional triangles. So the shape of the figure also changes slightly. And finally, evolutionary leaps. This is noticeable in our experiments when we try to create a new organism adapted to certain conditions. After long stable phases, the system suddenly leaps into a completely new state, like a digital Cambrian explosion. Now we're getting close to the main question. Why would someone need this? The honest answer is, this model has no practical application, at least for now. We're simply interested in developing it and learning from it as much as possible. Maybe one day this will help to assemble decentralized robot colonies, systems that aren't designed directly but evolve. Or perhaps this model will help test evolutionary hypotheses, just as one model was recently used to confirm that aging in organisms begins when a system loses its purpose to function. Even if that doesn't happen, we hope we can teach you something new about biology and computer science with GUCA. And like many good educational tools, you can just play with it, peek into the sandbox, run the simulations, and explore. Also, if you're feeling confident, you can download any genome from our website and edit the rules in it, and see what happens when you upload it back and run it. In our next video, we'll show how to create a new genome step by step, so it will be even easier to participate. And as you begin creating your own structures, you may discover that evolution often finds complexity more gracefully than we do. Stay curious and join us in exploring digital evolution.